Welcome everyone to a quick overview of lesson 1.11 from calculus, which is all about defining continuity at a point, which is a very fancy way of saying we're going to see if a function is continuous or not. Last lesson we talked about the three different types of discontinuity, and this lesson we're going to see is it continuous or is it not, and if it's not continuous, can we define which type of discontinuity it falls under. There are three requirements for a function to be continuous at a point. First of all, an corresponding y value has to exist for the x value we choose. The function has to be able to output something that corresponds to the input. In addition, the left-hand side limit and the right-hand side limit have to be approaching the same value, which is to say the limit itself exists at that x value. And finally, the limit and the y value that corresponds to the input have to be the same. So let's look at three different examples and see how that stacks up. All of these are piecewise functions, and most of the time you will be dealing with just the equations. I also wanted to showcase a table and a graph representation of these piecewise functions so we can visually see what's going on. So our first one here is for values less than or equal to 0, the function outputs e to the x, and for values greater than 0, it outputs the square root of x plus 1. If we look at the table, we see that the left-hand side limit seems to be approaching 1, the right-hand side limit seems to be approaching 1, and the value does exist at 1. We can double check this by physically doing the algebra ourselves. If I plug in 0 to both functions, even though the second part of the function doesn't correspond to 0, it ends at 0. So let's plug it in and see what happens. Well, e to the 0 is equal to 1. The square root of 0 plus 1, well, that's 0 plus 1, also equals 1. And again, we can plug in the 0 to this function and get 1. That exists, and if we look at the graph, it looks quite continuous. There is no noticeable breaks or discontinuity at all. This is a continuous function over its entire domain. The second function we're going to look at, there we go, is a sine and cosine graph, because why not? And the point of contention here is x equals 1. And we can tell that it does have an output. If we look at the chart, if I input 1 to the function, I output -1. Let's look at the limits. The left-hand side limit seems to be approaching 0, and the right-hand side limit seems to be approaching -1. Since those two values are not the same, it is discontinuous. Since the limit doesn't exist, we would say that this is jump discontinuity. And we can see that graphically, because if we look, our equation jumps down to continue. We can also check that algebraically by plugging in 1 to both of our functions, which would give us the sine of pi and the cosine of pi, respectively. Sine of pi is 0, and the cosine of pi is -1. Those values are not the same. Therefore, the limit doesn't exist, and it's jump discontinuity in this case. Let's clean that up a little bit. There we go. And let's move on to the last function here, which is this lovely piecewise function of 3 parts. So we have for x's less than 2, we output x squared. For x's that are exactly 2, we output 3. And for x's greater than 2, we output 2x. So graphically and on the chart, we can see that the limit does exist for 2, and it seems to be that both sides are approaching 4. But if we look at the actual value of 2, it is 3. And since the limit does not equal the value the limit does not equal the value, we call this whole discontinuity or removable discontinuity. I'm pretty sure I misspelled that, but that's perfectly fine. It's removable discontinuity. And that is represented graphically here. We can see the value exists, but it doesn't quite exist there. That is essentially it. If you have any questions, I'd recommend practicing. There's a lot of piecewise functions, so if you're not quite familiar with those, I would definitely ask your teacher for help. Other than that, good luck on your practice, and I'll see you in the next video.